everyone for joining today about wind generation, getting the right data to the right people at the right time. And kind of the purpose of this talk is to talk about our data journey. We have over 1,000 wind turbines, we have billions of data points, and I kind of want to explore how do we manage that? How do we make that accessible? What does that mean? And what kinds of interesting things are we doing with it? How are we going to scale it in the future as well as we bring on new farms and grow our renewable fleet? And I'll be talking a little bit about the application, the front end that we're developing as well to show off some of the cool data stuff that has been going on. So just a little bit of an introduction for myself, analytics engineer, electrical engineer by trade. On this team, I do data analytics and automation, data engineering, data architecture, a bit of UI design for our applications in OS. I like art, I like graphic design, and I like my puppy. Here you can see me trying to recruit her as my secretary, but unfortunately she didn't keep the job, so she just continues freeloading without earning her way through. I'm on the data and innovation team here at TransAlta. We are a team of engineers, developers, analysts, and data specialists. We deliver analytical, automation, and application solutions. Well, apparently I'm blocking some of the information. And our goal is to capitalize on the use of our data to operate safely, drive revenue improvements, and to save time. We're kind of like a data support group in a nutshell for the rest of the company, and we want to make it hard for them to not use our stuff. And a little bit about TransAlta. So we are a homegrown generation company. We were the first generation company in Alberta, early 1900s, so we're over 110 years old. Our first plant was the Horseshoe plant, which is still running today. It's a hydro facility, and we own over 75 facilities. We have expertise in hydro, wind, solar, battery storage, gas, and thermal coal. As of this year, we've phased out all of our coal in Canada or converted it to natural gas units, which really contributes to our target reduction in GHG emissions of 75% by 2026 from 2015 levels. We have own capacity of approximately 7 gigawatts, and of that, renewable is 2.8 gigawatts. Most of what we have is in Alberta. So for context, we own about a third of all the generation capacity in Alberta. We're the owner and major owner of TransAlta Renewables, and we have locations in Canada, the US, and Australia. Okay, so getting into it, why are we going on this journey in the first place? Like I said, we collect so much data, we haven't really fully leveraged it. We've been collecting data for a long time. We've had wind farms for a long time. And there's a lot of potential there that hasn't maybe fully been grasped. So we want to make it accessible, we want to draw insights, and we want to action it and enable others to work on it as well. So with that, we own 28 wind farms across Canada and the United States. You can see in this map here, I've kind of highlighted where they are. Most of them are in southern Alberta, some along the East Coast, and a smattering in the US. Together, we have a combined capacity of 1.8 gigawatts. For context, that can power 500,000 homes for a year. And we plan to double our wind capacity by 2030. So we're only going to be growing. Our wind fleet consists of over 1,000 turbines as of this year, each of which collects many, many different data points, has different sensors. And for each turbine, the data gets generated. And we want to make sure we store it, centralize it, prepare it, and use it in meaningful ways for our end users. So a little bit about generating this data, generating from our generating asset. Here's a wind turbine. This is a horizontal wind turbine. We call the whole thing a wind turbine. If you call it a windmill, you might get a little bit of a look from the field staff. They typically operate about the same, but we have different manufacturers and models that have slight differences from each other. On the outside, they look similar. On the inside, a little bit different. For example, some might have more sensors, have a different control strategy, or have different types of components, like different types of generators. And the opposite end of that is some might have less sensors. So we might not be collecting the right kind of data to perform the analysis we might be performing for a different section of the fleet. So we kind of have to handle that. Is there substitutions we can make with other information we do have available? Some of them, we don't really understand the control strategy fully because the manufacturer's a little bit secretive about that. I mean, that is their secret sauce, so it makes sense. So there is a lot of reverse engineering that has to go into understanding how these things work and how different components and parts of the turbine interact with each other so that we understand how this data is supposed to interact with each other. And some have different types of components. So like I said, with over 1,000 turbines, it would be nice to build, say, one model or one analytic that encompasses every turbine, but because they're a little bit different, that might not be possible, and that might not be the correct move since they might behave a little bit differently. When I'm talking about features, I'm talking about different sensors, different status points that we get from the turbine. So any kind of data point we have coming in. Some of those, the big ones are, of course, environmental. I mean, it is a wind turbine. So we record the wind speed, wind direction, wind deviation. It's the difference between what direction the wind is coming from and what direction the turbine is facing. And then things like temperature sensors, really it's mattered everywhere. So not only outside temperatures, but if you look at the cross section in the picture here, there's temperature sensors kind of all along that mechanical assembly so that we can track where a problem might be occurring. And then the turbine also uses those sensors as inputs for its own control strategy, typically. And then we also collect control and status points. So set points, parameters, state is the turbine on, off, paused, emergency, what have you, what kind of alarms are coming in and what kind of warnings. So lots of information there. And when we're talking about storing that data, I'll give you a second to play a game of what's the difference between these two pictures. On the left is what's available at the actual turbine, and then on the right is what we collect. So if we look at a green square is 10 turbines. It's one purple circle. For each turbine, we have maybe, say, like 100 different things available that we could collect about it. And then for each of those, maybe every 5 seconds or a couple of seconds, it might record a value. Some sensors might record it more often. For example, ones that have vibration sensing, you'd want to have a data point every second, multiple data points every second, if not even a higher frequency, in order to perform a proper analysis to see if something's going wrong. So lots of information available. I kind of estimate it to be around 700 billion data points over a year. In terms of what we collect, the biggest difference you can see from the first chart is the number of data points. We cut it down quite significantly to keep the proper context, but not be duplicating unnecessary information. And kind of how I explain that is for fast changing values, you want high frequency because you want to know what's going on. For something not changing that often, there's no point duplicating your information so that you have everything every 5 seconds. I mean, you could just extrapolate it later if you want to, but no point wasting your storage there. So for something like wind speed, we want to know quite often what the wind speed is because it's ever changing. For something like outside temperature, that's definitely overkill to be looking at it every couple seconds. I mean, even an hour is probably fine. We also cut down on the number of features that we pull in a little bit. And that's also, we're cutting down on things that don't give us extra context or isn't available. Some of these sensors or manufacturers don't let us access some of this information. But for the things we might not pull in, it might be a calculation based off of other data points or other sensors. So that's kind of something we can do ourselves and isn't really something we need to store in a raw format. But we do collect most of what's available there. And then you'll see some turbines we don't collect information for. Those are really technology limitations, especially some older farms. You know, these systems were never set up. It is a large barrier to go and set this up if we want to. If a site has 2 or 3 turbines, it's hard to maybe justify that cost. We also purchase wind farms, and they might not come with their own data connections. So for most of our fleet, most of our turbines, we do have at least some kind of information coming in. And for the ones that we don't, where it's important, we are setting up those data connections to have that whole view of the fleet. Or at least we're able to go and get that information somehow if it's not being pulled live like the rest of this data here. So in terms of all this data, so 130-ish billion data points we collect, maybe 20% of what's available, it's an estimate. We historically have stored that in a SQL historian, and that had kind of problems. First of all, it's so much data, so it takes a long time to query anything. It's not really structured in modern ways, like with cloud computing, Delta tables, where you can partition things and really optimize your queries. So typically the process would be we query our historian for the data we need. You wait a long time, you get it out as a CSV, open Jupyter Notebook or something, do some analysis, save your results somewhere. So it's a whole kind of manual process. And it really doesn't allow us to do that scale aspect of, well, we have 1,000 turbines, let's try to replicate what we do for larger chunks of them. And it's also a data silo. So we have other information we would like to have related to the site or these turbines. And that's not necessarily stored in this historian. So we kind of have to go manually find that information and put it together. And it's just a whole complicated mess. But now, instead, we use a data lake through Microsoft Azure to store the data, and then Databricks to process and transform the data. And Databricks has been really useful in that it's set up to work with Microsoft Azure very directly. We can mount it on our data, and we aren't actually pulling the data until we actually need it. We can also structure our data in Delta tables to properly, they mentioned, partition it or index things as we understand that the data is going to be used. So that speeds up queries quite a bit. And now it's actually just a lot easier to even go look at the data if we want to. Apart from that, so not only are we pulling a lot of information into our data lake, we are pulling other kinds of information like weather data. Again, this is a wind turbine farm. These are wind turbines. Weather is very important. So we're now able to pull in weather information for the site. We pull in user inputs. So for example, our operators and technicians keep track of kind of what's happening with the turbine, especially if it goes down, and provide comments, what has been replaced, what the problem was, things like that. And that's really useful information, especially when we think about, well, what if we want to predict these problems? What if we want to see if there's a common thread so that we can build a model or something around it, or even just do analysis over a problem and all that. So we store that kind of information in the data lake as well. We get system operator data. So that's the electricity pool price and various metadata on what kinds of components are in these turbines, what site they belong to, etc. And that's kind of the right side of this slide where we link data together through an asset hierarchy. Our asset hierarchy is really a series of tables where we uniquely identify every kind of thing and then link it to something else. So if you imagine, this is a very simplified version of it. There's a lot more tables and such that go on. But if you go left to right, everything has a one-to-many relationship. And if you go right to left, then we have a one-to-one relationship. So for example, if we're looking at a specific site, it belongs to a certain region in a certain country. And then it also has various wind turbines or other kinds of assets that belong to it. And then for each of those, say, wind turbines, they have various components that make it up. We can also go vertically with this chart. So for every site, we can see it's a specific kind of fuel type, and it belongs to a specific fleet sector within the company, and how we define our sectors. And what this does is it lets us link data through like a hierarchy system, as it is called, the asset hierarchy. So if we have data coming in for a wind turbine and we want to know the forecast data, then they're linked through their common site table because the turbine will inherit that it belongs to this site. And so we do that with all of our data that we have coming in. We actually kind of have like a data hierarchy as well to do this linkage so that you can link whatever piece of data, every piece of data that you have to something in this asset hierarchy, and you can get insights about it and link it to something else relating to it through these relationships that we've built. And then it's also nice because it serves as a source of truth. You know, we've had situations, well, it's very common. I have it right here, a piece of paper in front of me that has all the sites written out and some information about it and everything. And you go somewhere else and somebody has their own copy. And when does it get updated? When we retire a site or get a new site. So this is kind of meant to one day be the source of truth that is just like, you go here and this is true and this is what it is. And if something's changed, then you update this and then everybody sees the change. So it really kind of centralizes all of that data for us. Okay, and going into preparing the data. So now not only do we have it centralized, but we want to make it more usable, not only for us, but maybe for other people. And that other people part is this TA Spark. It's kind of like it's not really a coding language. It's for tracking data lineage. It's an in-house framework. It's built on top of or in PySpark. It's coded in PySpark. And it consists of reusable chunks of code to track data lineage and scale a repetitive operation. Sounds like a function, basically is a function. The idea is that you can perform complex calculations that will simultaneously answer the question, where did this number come from? It's kind of complicated talking about it like that, but the example I give is if you're looking at a financial report and a number looks a little bit off and you're wondering why, well, traditionally you will go maybe talk to who wrote the report. They will tell you where they got the data from. You do some exploration. And did it get overwritten at some point? I'm sure people have dealt before with really complicated Excel files and you're trying to track through where something came from. So what TA Spark would do is solve that. If that number was calculated using TA Spark, then it tells you exactly where that data came from, and it tells you exactly what transformations were done along the way. So I said it's like it's made out of functions. So those functions or nodes are these colored blocks here, the red, the blue, and the green. And they kind of do two parallel processes. One is they do what you actually want them to do normally, as you would like in PySpark or Python or whatever. And then on the other side, they provide this mapping of inputs and outputs. And this image that you see here would be what that output looks like. It gives you a graphical representation. So here we have two graphs, as they're called, which is a collection of nodes, and how they interact with each other. So you can see on the left side of both of these in the yellow, those are the inputs to this graph. And on the right side are the outputs of that graph. So that might be the number that you see in the financial report. So if you want to go see it, you would go open this up and then you can track through where it came from. And then you see the different color codings of these functions or these nodes within that graph. We have blue, which corresponds to the output of another graph. So you can go follow that through. You have red, which is kind of your main just general transformations or what have you. And then you have green, which actually links to a data source. So in this case, you can spot the green and you're like, okay, well, this is the path of where my data is stored. And you can go look at, say, the raw or the transformed or whatever data was used to get you that output. And so this is still very much in development. We use it for a couple of things. This one is specifically around 1/5 of the process on how we contract or how we calculate our contract availability with some of our manufacturers. So you can see it's quite complicated calculations. Previously, we would do those, I don't know, maybe like when you have to every few years. It's really complicated. Now it's been somewhat standardized and we can track that lineage and it makes it a lot easier. Okay, and going back to our wind data, we one of the ways we prepare it, the way that I like to use for my analytics, is we roll it up into a 1-minute time-weighted average. As it says, gets rolled up to 1-minute chunks. So here we have that image before of what data we collect, and this is the data that we actually transform into a 1-minute time-weighted average. So again, if we do a comparison about what's missing from before, couple turbines, we don't do this for because the data we get from them isn't the best. It's already rolled up It doesn't make sense to do a 1 minute average if we get 10-minute data. So it's not really like useful for those ones. Those ones are harder to do analytics on because it's not as high quality. But that's okay. For most of them, we get a lot of good data. And you'll see not a lot of features are used. And that's for a good reason. It's because these are the features we are currently using in our analytics later on down the stream. These are the ones really important, and you'll see later when I go over the power equation, these are the ones really important to how the turbine operates and looking at underperformance analytics for them. But this table is set up so that as we want to include more features and do more analytics and types of work, we can easily have it start streaming in and calculate this 1 minute time weighted average, get added to this table, and we can start working with that data right away. So there's that scalability piece. We don't have to go and reinvent everything every time we want to add something. This is got to change 3 values in a table somewhere, and then it should be able to pull in properly and calculate properly. And so the output of this is that we get a table like this. Everything is nicely aligned on a 1 minute timestamp. You have your site, your turbine, bunch of features about it. You can do calculations between those features, and it becomes really easy for not just someone like me, but anybody else who wants to know anything about their site, what's going on at that time. If they're troubleshooting, if they see something weird, they can go look at it, and it's just a lot easier. Yeah, just in terms of how many data points go into this. So normally we get like 50 million a day. That is, what are we pulling a day? Something like 3 gigabytes of data. We transform it into 15 million data points a day, but that's not 15 million rows. It's only like 1,500 rows a day, which is great. And then everything nicely put into columns. Sorry, 1,500 per turbine for all the turbines. So this is really useful. A lot easier to work with than raw data. But we also have to think about the data quality when we do that. Like I said, I use this for checking the performance of the turbine. So it becomes really important to know that the data is good and trusted versus there are data issues. And what we do for that is for every feature that we're using, it has really specific defined characteristics on how to roll it up. And this is where subject matter expertise comes in. It might seem simple, but there's a lot more to it. There's a lot more specifics to different kinds of sensors that we pull in and how we have to deal with them because of their unique characteristics. But 2 simple examples, wind speed and wind direction. So when we pull in wind speed, like I said, it changes all of the time. And if we roll it up into a 1 minute average, what our historian would do is fill in any gaps in data. So you can see in this data, we have some values for 10:57 and some values for 11 o'clock. So 2 minutes of no data. Because we know it's wind speed, we know that those 2 minutes where we have no data is basically garbage. I mean, we don't want to forward fill that or interpolate it or anything. We can look at another turbine and see what the wind speed is there and if they recorded a value. But for this, what we trust is the data that we have, and we want to leave a gap for those 2 minutes and say, there's nothing here. And there was a big frustration I had with the historian, for example. It linearly interpolates between these points because it can't really catch those gaps. So now wind speed is a lot cleaner, and we only have it for trusted times. Another example is wind direction. Seems obvious when you look at it. If we're hovering around the north and we're measuring things in degrees, 0 to 360, if you average that as you normally would, you're getting a south direction, 180 degrees. So you actually have to use a proper sine cosine function to average this out into a true degree average. And that was another thing that the historian wasn't really able to do other than with a lot of tinkering and complex queries. So this becomes a lot easier when we're using Databricks and PySpark. Then for each feature in each day, we collect information about the data quality, things like the percent of bad data, the percent of gaps in the data, what's the most common value. And we're collecting things that tell us if we should trust that or not, basically. So we can differentiate data issues, and then we flag it to the relevant groups to look into. We have a field IT group that looks into actually getting the data from the site to our systems for the first place. And then the result is clean, trusted data that can be used for further analytics. Okay, and from there, we can get into actually using the data. This is kind of misleading, the top bar, because it's not really a linear path. The use cases really come from different points along this path. So we want to aim to encourage other people to use the data at various steps for what makes sense to them. For example, after we centralize the data so it's all in one place, plant engineers might find that useful. Technical services who want to look at this kind of raw format of the data, but also see everything that's going on. Users after preparing the data, plant engineers, analysts, finance, technical services, field IT, like I mentioned, field IT. And then we also have users with specific use cases that I'll be going into after this, which is wind technicians, wind operators, management. They might want to look at their overall site performance or specific KPIs. And compliance is an important one to make sure that we are following regulatory requirements. A lot of the time we have to use the data to back that up. And if you have it in a nice dashboard and specifically built for that case, it becomes a lot easier than going to have to manually find it yourself. And the thing with this is that more people use the data along this path, the more clear data requirements for new sites become. I have a lot of dust in here. Sorry. Yeah, the more clear data requirements for new sites become. Sorry, one second. Okay, that should be good. I think I ate one of Chewy's hairs. Like I mentioned, we're planning to expand our wind fleet quite a bit. I think the target is to double our wind capacity by 2030. And with that, with new contracts and new constructions, the more we know about what data we need, the easier it is to structure these deals and to talk with the manufacturer about our requirements before it becomes too late and we realize that maybe the data we want to use isn't available. So it kind of becomes a loop where the more people that use it, the better it is for everybody, for the whole company. Okay, and now I'll jump into some specific use cases. This one's more of an engineering slide if you're interested in that kind of thing. So digital twins. Digital twins are meant to map out what a turbine should be performing like by using the data so we understand what it should be. Sorry about that. So we understand what it should be performing like. So here's our general wind turbine power equation. And it tells you a lot about why the turbine operates how it does. For example, we say that wind speed is the biggest factor hopefully this goes away. We say that wind speed is the biggest factor on power production because you can see it has a cubic relationship in this power equation. So it has the most significant relationship as wind speed increases. It also has a relationship with air density. Air density itself doesn't change that much, maybe a little bit with elevation and pressure and whatever. But so you might be thinking, well, why don't you use a different fluid like water, just 800 times as dense as air? Congratulations, you've just discovered a hydro turbine. It's also the reason a hydro turbine will always produce a lot more power than a wind turbine. If you've ever been thinking about why wind turbines keep getting bigger and bigger, it's because of the swept area relationship, where power is proportional to the radius of the swept area of the turbine. So theoretically, if you're doubling your swept area, or if you're doubling your radius, then you should be quadrupling your power output. In the picture at the bottom here, you can see one of the blades on the ground before construction of one of the sites that we had commissioned late last year. So we went to visit it before it was fully built. It was hard to get the whole length of it, so I had to turn about 90 degrees to even look at it. But that whole blade is 70 meters in length. You can kind of see it compared to that big SUV there, that the width at the root is about the size of a big SUV. And the picture on the right, that's a turbine half the size. So if you're ever down in southern Alberta and you see some turbines that look twice the size of every other turbine you've seen around them, it's from this new site. They're 4.8 megawatt machines, so pretty significant. Okay, and back to data. As I said, we have a very strong relationship between power and wind speed. And that's what is typically called the wind turbine power curve. Manufacturers give you this. This is what you look at to look at your expected operation. Sorry. This is, so you can see the cubic relationship as we start increasing in wind speed over the x-axis. And then it starts to tail off. Theoretically, we can keep that cubic relationship, but then your wind turbine would spin out of control and probably catch fire. So most of them, well, actually, for sure, all of them, unless something's going extremely wrong, start to curtail themselves to this maximum possible power, and then they operate within that region most. So what the question we're trying to answer with digital twins is, are these red points that I've highlighted on this power versus wind speed chart, are these normal operation, or is this some kind of underperformance? And this average was created, you can see the opacity scatter plot kind of behind the average curve there. Those are our 1 minute data points over, I want to say a week or 2 weeks I did there. So there is quite a bit of noise. So it's hard to tell, is this just noise because, you know, the wind speed is changing a lot within a minute or something else, or is actually something going wrong with the turbine at that time that should be addressed? So what we do is we realized instead of just having a relationship between power and wind speed, we can make multiple relationships between all of these variables in the equation. More sensors that actually feed into some of these variables as well. It's not just limited to this. And it kind of becomes a multi-dimensional problem that you can lay out in a 2D way. And that's what this right side is here. So at the top, you can see your blue power curve, kind of similar to what we had earlier. But at the same time, if we're looking at wind speed, we can see what we expect the coefficient of power to look like, what we expect the rotor speed to look like, what we might expect the pitch angle to look like. This is just an example I found online. As I said, every turbine operates a little bit differently. So we look at our data and we generate this twin curve for turbines that we know are operating correctly. That's kind of the example you see down here, where you can see the twin curve is in pink, and then one of our turbines is behind it. At this point, you might be thinking, well, this kind of seems like a machine learning problem. You have all these variables, throw them in a model, get some kind of output. It can be eventually, now that we've come to this point. The big kind of like technical knowledge part of this was understanding what it means when we see something different. Does it actually mean it's significant? Does it mean that we're averaging data incorrectly? This comes back to the point of why it was so important to clean up this data properly, to make sure that we're looking at what we know is correct, so we can isolate that this is actually something behaving differently. And even then, it's such a multivariable problem that looking at the pitch versus wind speed curve here, and you see a deviation. I mean, just off the top of my head, I can think of 4 different things it could be. But that's not necessarily all of the different things it could be. So how can we create a machine learning model if we don't know what we're looking for and what we're expecting? And that's really the knowledge base by doing this physics-based analysis first that we've been building up, so that we now know what we actually want as an output from this. Okay, and the last case I'll go into is icing. So ice on turbine blades, you can see it in the picture. It's kind of similar to what happens with airplanes. Honestly, these blades are pretty similar. They just kind of rotate along the edge so that they spin in a radial direction instead of propelling itself forward as the plane would do. So with icing, what happens is that weather conditions are prime for ice to form. Ice will form on the blades. The aerodynamics change, and then production is affected and power output will decrease. So it's kind of a time-based problem where your weather conditions are prime for it, ice forms, something happens. It's kind of a two-piece on either end. And ice on turbine blades is a really common problem in Canada. I imagine most of us live here and realize that it gets really cold really often. And our operators have to deal with that. Also with our Ontario sites and on the eastern coast, they have to deal with that, especially where it's more humid. And they have to decide if they want to stop the site or keep it running through icing conditions. Some of the considerations they have there is if they stop the site too early, they lose revenue because we're not producing and they risk icing up the site. For example, what happened with Texas last year, the year before, when they had that big ice and winter storm, part of the reason is if you ice up your turbines when they're stopped, you might not be able to start them again for a couple days or even a couple weeks. So that's something you have to consider. If you have that power demand, how do you weigh those options? And then there's the safety risk of stopping the site too late. So I couldn't find the picture, but if enough ice forms on these and they're spinning, you get some centrifugal force and it lobs pieces of ice across the way. And that's extremely dangerous. They can be, huge chunks of ice for not only, it'll hit equipment, but it'll hit people. So you don't want anybody around when these icing storms are going on. And then it's also causing mechanical stress on the turbines. You have a force imbalance. If you have more ice on one blade than the other, you get some vibrations, and that really wears down the components and can shorten the life of certain components or of your turbine in general. So they have a lot to think about, and then they have a lot of data that they used to have to look at to make their decision. And that's part of what we did. So we came in and we consolidated a lot of the information that they had into one place so they can make their decision. They can make their decision a little bit easier and less stressful to have it all in front of them. So what you're seeing here is a chart, time axis on the bottom. We have a line for what now would be in 2 days in the past and 1 day in the future. So if we're looking at the 2 days in the past, what we do is we track what power we're producing at the site. So we only know that, real time and in the past. And then we're also tracking what we expect our power to be. So if we go back here, that's kind of this production is affected part that happens after weather conditions are prime for ice to form. And we have this threshold to say where it's highlighted blue, okay, well, we're deviating from what we expect to produce so much that there has to be something external affecting why we're not producing what we should be. And then the other part of this is that ice probability. So this is the red part in the background. What we've done is we've calculated percentage-wise, what's the probability that ice will start to form? Not that it is forming, it's that weather conditions are prime for it to start forming. And now you can see kind of that relationship, weather conditions to production. So our ice probability or weather conditions became a lot worse. And then our power started deviating shortly thereafter, whether a few hours or what have you. And so now this, looking at it, an operator can see, okay, well, this seems to be going on, and make that decision a little bit more stress-free. What they used to do is go on various forecast websites, look at different forecasts, kind of determine for themselves what they think the chance of it icing up is. Some sites have a webcam, which is nice. You can actually see if it's snowing or raining or what have you. So they would look at all those sources, and they would have a separate power meter to see what the turbines are actually producing. It was just a lot to do at once. And in the case of a severe quick ice storm, minutes might be integral, especially if somebody's at site, to make a decision. So having this information makes them able to kind of look at that a little bit better. And then the other part that we are trying to do for them is give them a prediction of ice of an icing event that would be happening. So if we look at from the now to the +1 day in the future timeline there, we do have an icing probability calculated, But we don't really know right now what we expect the power to be, or are we deviating from what we expect the power to be? Has ice already formed? Is ice still on the blades? And we've been working with AltaML over the past year and a half on a couple of ideas surrounding this idea. How can we create perhaps a better power prediction in the future related to specifically ice on the blades, so that the operators actually have an idea this kind of thing is coming. And lastly, I'll go into our actual application. So a lot of what we do, if there is a use case for it, then we will implement it. Not everything needs its own screen. Not everything needs its own fancy visualization, right? When something comes in and it's to be safe, it's to bring revenue, or it's to save somebody time, we build it in a way that makes sense for that specific use case. And if it makes it to a front-end interface that somebody needs to use, it makes it into this application called GenOS. For wind, our primary users are wind operators and wind technicians. But we also have this set up to be for every fuel type. You can see the icons at the top there. And yeah, it's a tool for transforming data into action. We customize the tool and the platform to suit the specific needs of the users. On the right side there, you can see the Wind Control Center. This is just part of their screens. They have another like 20 screens or something. And you can see GenOS is up on there, and that's that icing chart. So they have it right in their field of vision, and they can look at it and reference it whenever they want to. They also have a smaller screen on one of their monitors where they do some of the reporting for down turbines. And we also have a mobile view. So a nice consequence of creating a mobile view that we didn't actually anticipate is that technicians, when they actually go to the turbine and fix something or do something, they can enter a comment about it straight into the application. And so now we're kind of closing that loop of getting more information from the site so that we can better serve them, like help us, help you. And there's a really big aspect of trust that we're building with our customers here. We never want to be pushing a solution on somebody that they didn't ask for. What we do is we work with the people that have a use for data, and then we help them figure out what they want to do with it. Part of it is even people understanding what data they have available. Some business units don't really have that visibility, so that comes back to even centralizing the data and showing them what they have. And we're able to build innovation that way by encouraging people to take ownership of their data, and then we help them get to where they want to go. And that's pretty much it. Yeah, so thank you for coming to my talk. Some takeaway points is lots of data can get really unwieldy, and it's really important to know your data and know your audience. The knowing your data, especially so that they trust you. And being really, I guess, meticulous or really intentional at every point of the process when you get your data to when you're actually using it will encourage other people to bring more ideas and build the system up better. And then you can also scale things as you are building up your fleet like we are.
That's great. Thank you so much, Natalie. We have time for some questions, and some people have already posted them. So again, if anyone has questions for Natalie, please put them in the comments and we'll bring them up on screen for Natalie and everyone to see, and she can answer them. So we'll start with the first one. And I guess Ian is asking, what are the limitations of the lineage graph that you'd get out of an orchestration tool like Airflow or transformation tools like DBT that led you to rolling your own?
Yeah, I think we've tried a couple of data governance softwares and a couple of ideas along the way. And we just have, I guess, specific use cases that made it difficult. Like even when we tried to bring in other tools or software, there was so much setup involved with them. It kind of became like, well, we might as well do our own. That's also part of the reason we created GenOS. There's a lot of other analytics tools that technically can do the same thing, but it was so much work to even integrate that. It becomes, well, we might as well make our own, and then we understand it inherently. We have the proper documentation, and we can build it in a way that we want to without any limitations that might come up. Okay, in the data collection stage, you mentioned different sources and different sampling intervals. Was it a challenge to reconcile and work with this data in later stages, and how timing plays a role in general in your application? I would say the different sampling intervals were pretty good as long as we understood how they were done. So we have a whole team that handles actually bringing in that data with the sampling intervals, and just by talking to them and understanding how it works, we were able to code that into our practices and know what to expect from data. So it was a little bit of a challenge there just to get that information to understand how this works, but now it's sort of been codified, which is nice. And how does timing play a role in general in our application? It plays a very important role because when something happens at a turbine, you do want to know everything that's happening at the same time to see why something is actually happening. So like that 1 minute time weighted average was really important to see what's maybe changed in the 5 minutes prior to that, see what's changed in the past 10 minutes. And it becomes kind of like a time series problem in that case. Hi, we are trying to build a wind generation forecast and simulation tool. Based on your experience, what are the most important features that can predict wind generation in terms of megawatt hours? Right now, we are using month, hour, temperature changes. So air density for sure. Elevation, if you don't have a direct air density measurement. And I would just play around with different forecasts to see which ones actually align with your site the best, to see which ones are the most accurate, because some are definitely a little better than others. Okay, were the ice events identified via some sort of operator log, or were they obvious enough to pick out from the raw data trends? Historically, they would sometimes record event logs when they shut the site down for icing, if they had time. So sometimes they would miss it. Right now, they use that chart, and we have a button there so they can easily put in a log for it. So they're keeping track of that information. I'm wondering how often icing events occur and how much of a problem that would pose for regular power for the turbines in winter. It's a good question, how often. From what I've seen, maybe, I mean, it depends on the season, maybe sometimes a month. Your really bad region is when you have really high humidity and you're kind of up to that minus 10% range. So it's wet, and when ice contacts something, it'll start freezing up. The duration is a problem. If your event is going on for, or if your ice storm or cold weather and high humidity is going for a long time, you're probably going to build up a little bit more ice. But in terms of how often, what I've seen in January was at least like 5 times or something like that. And again, it's sometimes hard to tell because sometimes it's not long enough to actually start affecting production, or significantly enough that we would turn off the site. Okay, does our mobile GenOS app allow operators to access real-time sensor data as well, like the 1 minute time weighted average from data lake? In GenOS, we pull in 15-second data, live data, for some key features that they want to see. Otherwise, in the icing chart, we pull in 10 minutes because we don't need the 1 minute granularity necessarily. And then we'll be working on, as the use case comes up, if 1 minute makes sense, we'll bring in the 1 minute. So it really depends on what they need to know and how quickly they need to know.